We are transcribing toy language tutorial of LLVM MLIR tutorial, and we have done until chapter 4. Today I'm going to transcribe code for chapter 5. It's partially lowering to low-level dialects. We'll convert to some of our high-level language specific semantics towards a generic affine-oriented dialect for optimization. So the tutorial itself is here, but we are not going to see the source code in this tutorial, but we will look at the code diffs. To summarize, this example is a processing input program. Looks like this. This is the MLIR program, and it'll be converted into a program using lower level dialect like arith for arithmetic and affine. The prefix here is the name of the dialect. So we are lowering partially this time. So this time we are not going to get any machine code, but we are partially lowering because this part is not done yet. We still have a toy prefix, which is the toy dialect we created. So this is making us impossible to convert this program into machine language. This is going to be converted to machine language in the next chapter. So let's continue. One example. I think I can give you one example. First, let's open up the source code. The toy language looks like this. User-defined function. And also it has tensor declaration with tensor literals. And we can call user-defined function. And in the user-defined function, we can call internal function called transpose. And also it has element-wise multiplication. So this part will be converted into a loop like this. So it's loading data from each tensor and multiplying element and storing to a new tensor. So we will see how this is going to be converted from this one to these codes. Okay, let's get started from the top level file, toy.cpp. This file. Also, I made a diff between chapter 4 and chapter 5. We finished with chapter 4 until episode 6, so if you want to take a look at what we have done, you can look at 6 episodes. I started from chapter 2 because chapter 1 is about the creating AST, which part this part is I'm quite familiar with. So here we are here now, so we're gonna create a diff between these two chapters. And here we have it. So let's just start from the toec.cpp. This one is added, dump MLIR Affine. And the new line was added. We're going to create a new path manager here. Oh no, well, we already created the path manager. We're simply using it. Apply path manager CL options. We already have it. Check to see what granularity of MLIR we are compiling to.
Check to see what granularity of MLIR we are compiling to.
So emit action is here. Emit action. If the emit action is greater than dump MLIR Affine, then we're gonna dump. We're gonna do lowering transformation. And then adding legacy passes into an if statement. And we have some new processing here. It's lowering to Affine. We are partially We will create this one soon. View, play up, post lower. Post lowering only for font up. Canonical. We already have one here, but it looks like after lowering to Affine pass, it looks like we need to do it again. Commands of expression animation. Oh, this was wrong. Uh-huh. Using lowering to Affine. Oh, enable opt. I see. I need to remove the enable opt. Okay, we are done. Don't put MLIR, fine. Okay, we are done with the toyc.cpp. I skip this file for now because it's longer, and I guess it's better to transcribe the source code in a top-down fashion. Constant up dialect.cpp, constant up. And we're creating a new function for creating the path for LowerToAffine in passes.h. This one is extending our input argument type for print, because now we have a F64 memref for additional type. We have to change this part because after the lowering, F64 tensor becomes F64 memref. So the print op should be able to accept the additional type, which is F64 memref. Okay, we're done with this file. It looks like we have a CMaker file left. We have a new file called LowerToAffineLoops. And it depends on include directories, property, dialect, oops, global, transcribe it. Looks like we are adding libraries related to dialect libraries. And then switch order. And then we need the MLIR support. Okay. We're done with the make list file. Now it's time to open up new folder, chapter 5, and then we'll transcribe the new file, LowerToAffineLoops. This is the original source code file on the left side, and on the right side we have our source code. But before to transcribe this file, we have to add it to MLIR folder. Add new file. LowerToAffineLoops.cpp. Built-in dialect. Toy dialect. Toy classes. Toy-to-affine rewrite patterns. Convert the given tensor type into corresponding.
Convert the given tensor type into the corresponding MLIR type.
In the previous episode, we have done type inference, and after all type inference applied, the test type should be just providing the shape dimension, for example 3 by 2, and also get element type. The element type is necessary to create the memref type.
Insert an allocation and delocation for the given memref type.
Make sure to allocate at the beginning of the block.
Make sure to allocate at the beginning of the block.
You may wonder what the block is. Block is something like block means a function block. So this is a user-defined function. So here we have a region, and in the region we have the block. This one is block. We get the parent block and so the log op is an operator, and the operator is going to be moved before the parent block's front. I don't really understand this code yet, but looks like we have to have some example input to understand what this is. I think it's creating a log up and dialog up at the beginning of the block and at the end of the block, respectively.
Make sure to deallocate this alloc at the end of the block. This is fine, as toy functions have no control flow.
It means we don't have any control flow, so dialog up is always executed without any control. So parent block is get block. A log is created and in the parent block, and we are moving a log to the before the front and before the back.
This defines the function type used to process an iteration of a load loop. It takes as input an op builder and range of memref operands, corresponding to the operands of the input operation, and the range of loop induction variables for the iteration. It returns a value to store the current index of the iteration.
function type used to process. I don't really understand this yet. We will come back soon. Loop iteration function is here. Let's see where this is used. Lower to up loops. Binary lowering. Okay, let's do like this. Instead of implementing all of these functions from start to end, we will first transcribe a function signature and then function signature with the empty body, and then we will come back from top down order so that we understand how this, why this is made and how this is used. So I'm not going to type in this one, but just skip it.
토이 토킹 리리터 패턴즈 비너리 아퍼레이션즈
conversion pattern. I guess the conversion pattern is base class for conversion patterns. Type conversion, another use is specific to conversion framework, such as patterns of this time can only be used with the apply methods below. Conversion pattern. Get converter, get type converter, and get type converter.
Base class for the conversion patterns. This pattern class enables type conversions and other uses specific to the conversion framework. As such, patterns of this type can only be used with the apply methods below.
Binary of lowering has two type parameters. We need to understand what these are. I don't know, so we'll ask the Copilot. That is the operation to match. Okay, so this is basically matching add up to replace it with the add f up in the arith dialect. So conversion pattern is converting add operation into arith add f up.
토이 토킹 리리터 패턴즈 컨스턴트 아퍼레이션즈
this one, toy to affine, rewrite patterns, functions.
토이 토킹 리리터 패턴즈 펑크 아퍼레이션즈
So it looks like we are defining match and rewrite function for each operation. Return operation. The lowering pass for return operation. because we don't have so many lines, I'm gonna just type in here. During this lowering, we expect all function calls have been included, have been inlined.
During this lowering, we expect that all function calls have been inlined.
I don't really understand this. Let's take a look at what return looks like. Chapter 5. Return. Okay, just return. Just return. Why? Oh, I see. Now I understand. What it says is during this lowering, we expect all function calls have been inlined. So because all function calls are inlined, we should not have any return operation that is returning actual value. For example, this one is returning value, but this one is not. For all functions returning values, we are inlining. In other words, we are replacing this line into this function body. So the return is not the return statement is not necessary anymore. But here we have a hidden return that is not returning any value but marking the end of the block. So here we are simply replacing toy.return directly to func.return by calling replace up with new up.
토이 토킹 리리터 패턴즈 트랜스포즈 아퍼레이션즈
So we are creating toy to affine lowering pass. In the lowering pass, we are probably using the patterns defined until now.
This is a partial lowering to affine loops of the toy operations that are computationally intensive, like matmil for example, while keeping the rest of the code in the toy dialect.
Define explicit internal inline type ID. The dialects we are using. Memref.
Create a pass for lowering operations in the affine and std dialects.
코어 서브셋 오브 더 토이 IR 이 지맥물.
Yes, this one was in the toyc.cpp. We have seen it. So it looks like this one is the main function. Create the lower to affine pass. Toy to affine lowering passes. So this is the main part. For each operation, this is executed. So let's see the implementation here.
first thing to define is the conversion target. This will define the final target for this lowering.
Okay, this is the final target.
We define the specific operations, or dialects, that are legal targets for this lowering. In our case, we are lowering to a combination of the
Affine, Alice, Punk, and MLIR dialects.
Okay, add legal dialect. Built-in.
We also define the toy dialect as illegal so that the conversion will fail if any of these operations are not converted. Given that we actually want a partial lowering, we explicitly mark the toy operations that don't want to lower toy print as legal. Toy print will still need its operands to be updated though, as we convert from tensor type to memref type. So we only treat it as legal if its operands are legal.
Okay. Some illegal dialects. Adding dynamically illegal op. We're going to check the operand type. None of operand types are So none of operands should be tensor type. Yes, as we expected, we are using the pattern.
Now that the conversion target has been defined, we just need to provide the set of patterns that will lower the toy operations. With the target and rewrite patterns defined, we can now attempt the conversion. The conversion will signal failure if any of our illegal operations were not converted successfully.
Okay, I'm gonna finish today morning's broadcasting until here. To summarize, in the toys.cpp we have created a new enumeration for emit action. It's dump MLIR affine. If dump MLIR affine is used, we are using is lowering to affine, and if is lowering to affine is used, then we're creating lower to affine pass, which is going to be created in the LowerToAffineLoops.cpp. This one is creating a new class, toy to affine lowering pass, and for each operation we are creating conversion target, and for the target we are adding legal dialects and also illegal dialects, and also dynamically adding legal up. We add the print up as a legal up only if the parameter, none of the parameters is having tensor type. Then we are adding patterns for lowering transformation. We have defined lowering transformation for add constant func mul print return transpose. These are all defined above, but we didn't actually implement. Today I feel a little bit tired, so I'm gonna come back soon after taking a rest. Okay, thank you very much.